Hey guys, so for this week we're going to be looking at two specific experiments, one being the sieve analysis, two being the specific gravity analysis of aggregate. So the aggregate we're going to be working with today is going to be a mixture of our limestone aggregate and then also some just beach sand. So this is a very typical mix for super pave, which is a type of asphalt, and then also our obvious concrete mix, which we'll see in a few weeks. So the first test is going to be the sieve analysis. This test basically separates the particle size or the aggregate size to allow us to show a particle distribution graph, which then can be compared for various types of mixes and designs and to provide a quality control of the specific aggregate mix that you're using for our concrete or our asphalt design. Now the other test is called the specific gravity test. And this is a very easy test of just using different weight-volume relationships to estimate or to determine this index called the specific gravity, which is a indication of the material's density compared to water. So we use the bulk specific gravity, and we also can calculate the saturated surface dry specific gravity. So both material properties are important to calculate, and again, these are used to act as a quality control in specific type of designs. And again, look back to that previous lecture, the PowerPoint lecture, to get a little bit more background information on those two.
Okay, so recall that the sieves are really just mechanical filters of varying sizes that allows us to separate the particle sizes by weight of our total aggregate. So again, the aggregate is made of various types of sizes of particles, from gravel to sand to fines. So these separate them and provide a standard way of creating that grain size distribution plot. So this is going to be our first one. This is the pan, and this is basically just a bucket that's going to capture everything. So this one will be on our bottom. Up next we have our 200 sieve. The 200 sieve, you can see here, has a opening size of 0.075 millimeters. So that will go here. Up next we have our 100 sieve. This has an opening of 0.059 inches or 150 micrometers. Then we have our 50 sieve. This has an opening of 0.3 millimeters or 300 microns. Now what you may notice is there's already some residual stuff stuck in here. This is going to be a source of error. If we were doing this for research, these sieves would be completely clean. We're just going to assume that any material stuck in there right now is going to remain stuck in there at the end of the test, and it's not going to affect our total mass of the aggregate we're using. But that could be a source of error. The next sieve you can see gets a little bit bigger. This is number 8 sieve, and this has an opening of 2.36 millimeters. So now we can actually start seeing that it just looks like a grid pattern. Okay, up next is our 4 sieve. Our 4 sieve has a 4.75 millimeters. You can see it looks a little bit bigger, and this is going to separate our sands and our gravel. Now these next 3 you can see get much, much bigger. These sieves aren't actually called by numbers anymore, so this is just a sieve that corresponds to 9.5 millimeters. This sieve corresponds to ½ an inch or 12.5 millimeters. And then this sieve is 3/4 of an inch or 19 millimeters. This is going to be the biggest one. So again, we have them all stacked here in ascending order. So the largest is going to be on the top, and then the material is going to filter through, and eventually we'll get to the pan where only very, very small dust is going to be held. So first you have to take the empty mass of each one of these sieves, and I'll provide that in the data sheet. We're then going to take our material here, and that material is going to be passed in through the top. We'll put it through the shaker in the back corner, and then we will take the mass of each one with material accumulated on it and subtract the two to calculate the amount of material stuck on each sieve, which will then provide us the grain size distribution plot.
Okay, so now we have our stack of sieves here after they've been on the shaker for about 10-ish minutes. Now we're going to take it apart, measure each mass, and then subtract the empty mass of each sieve, and that's how we can get the mass retained on each, and then eventually the percent mass retained for each sieve. All right, so after we've taken apart the sieve and taken the mass of each one, we can see how each sieve retains the particles that are roughly the same diameter as what it is as the opening size. We can see relatively a lot of material on the larger ones, and then this number 50 sieve has the most material retained on it, suggesting that this is a primarily sandy material. Now we can see how we would have our regular aggregate here, and the resulting constituents depending on particle size. Okay, that's it for the sieve analysis. Up next, we're going to take only the material passing our number 4 sieve, and we're going to perform the specific gravity test. So it'll only be done on the material 4 sieve and larger.